We throw around the words mass and weight all the time, pretty much like they're the same thing. But in the world of physics, whoa, they are not even in the same ballpark. And confusing them, it's not just some tiny mistake, it's a huge cosmic level misunderstanding. So, you know what? Let's settle this debate once and for all. Okay, let's start with something you probably see every single day, your bathroom scale. That number's staring back at you in the morning. What is it really telling you? Are you looking at your mass or are you looking at your weight?
And I bet the answer is not what you think, because what that scale is actually measuring, well, it gets right to the core of the difference between the actual stuff you're made of and the invisible force that's constantly pulling you down toward the center of the Earth. All right, let's dive in. We're going to break down the science and finally separate these two ideas for good. Okay, so let's put them side by side. The differences are pretty stark. First up, mass. Think of it as the amount of stuff, the matter that makes you you. And here's the kicker. That amount never, ever changes, no matter where you are in the universe. Now, weight, that's a whole different story. It's not stuff at all. It's a force. It's the pull of gravity on all that stuff. And because gravity can change depending on where you are, say the Earth versus the moon, your weight can change too. Which leads to this wild idea. You always have mass, but you can actually be completely weightless. How cool is that? This difference is so huge, so fundamental, that we don't even use the same tools or the same units to measure them. For mass, we use kilograms, kg, and we measure it with something called a pan balance, which is basically just comparing one object to another. But for weight, we use a totally different unit, the Newton, and a different tool, a spring balance, which measures that gravitational pull. It's like they're speaking two completely different scientific languages. Okay, let's get just a little bit nerdy here for a second. Mass is what's called a scalar quantity. That sounds complicated, but all it really means is that it's just a number. It has a size, a magnitude, but no direction. So a 10-kilogram dumbbell is just 10 kilograms. That's the end of the story. Weight, on the other hand, is a vector quantity. And what does that mean? It means it has both a size and a direction. Your weight isn't just some random number. It's a force that is actively pulling you in a very specific direction, straight down towards the center of the Earth. All right, enough with the definitions and the theory, right? Let's make this stuff real. To do that, we're going to take a quick trip through space to see exactly how this works in practice. This right here, this is the golden rule for our little trip. Just burn this into your brain. Mass is constant. Weight changes. Got it? Okay, let's see it in action. So let's imagine we have an object. Could be a person, could be a big rock, doesn't matter, and its mass is a nice round 100 kilograms. Here on good old Earth, our planet's gravity pulls on that mass with a force of 980 newtons. That's our starting point, our baseline. Okay, now let's hop in our spaceship and take that same 100-kilogram object to the moon. And get this, the mass, it's still 100 kilograms. Not one bit of stuff has changed. But the weight, because the moon's gravity is so much weaker, the weight absolutely plummets down to just 162 newtons. See that? Same mass, but a completely different weight. And for our final stop, let's drift out into deep space, far, far away from any planets or stars. So what's the mass? You guessed it, still 100 kilograms. But the weight? It's a big fat zero. 0 newtons. This, my friends, is what true weightlessness is. You're still all there, all your matter is intact, but there's literally no gravitational force pulling on you. Okay, trip's over. Let's bring it back home to Earth. That journey was a fantastic way to see the difference. But this next puzzle I've got for you, it shows how this whole mass versus weight thing can actually matter right here in our everyday lives. So here's the brain teaser. Let's say you go to the store to buy 1 kilogram of sugar. Now my question to you is, where would you get more actual sugar for your money? At the North Pole or at the equator? Think about that for a second. The trick to this puzzle, you see, isn't really about geography. It's about physics. And the answer depends entirely on how you measure that 1 kilogram. Okay, scenario 1. We use a pan balance. This is that old school two-sided scale you see Lady Justice holding. It works by comparing your sugar to a known certified 1 kilogram weight. Since gravity is pulling down on both sides equally, it totally cancels itself out. It doesn't matter where you are. With a pan balance, you'd get exactly 1 kilogram of sugar. No more, no less.
But what if we use a spring balance? You know, the kind with a hook that you hang things from, or even your typical bathroom scale? This scale doesn't compare anything. It measures the downward force, the weight. And because it's measuring that pull of gravity, it is absolutely sensitive to tiny changes in that gravitational force.
And that brings us to the answer. Fun fact, gravity is actually a tiny bit weaker at the equator than it is at the poles. So if your grocer is using a spring scale, which measures weight, you'd need a little more sugar, a little more mass at the equator to make the scale read 1 kilogram. So the savvy shopper would buy their sugar at the equator. You'd get just a smidge more for your money. Whew! Okay, we have covered a lot of ground, from vector quantities to the economics of buying sugar. So to make sure this all sticks, let's lock it in with a final, super simple cheat sheet.
All right, let's do a quick fire round. Ready? Mass is the matter, and we measure it in kilograms. Weight is the force, and we measure it in newtons. Mass is always constant no matter where you go. Weight changes with your location. You measure mass with a pan balance. You measure weight with a spring balance. And finally, mass can never ever be zero. But weight, yep, it can totally be zero. That's weightlessness. Bam! That's everything you need to know.
So, I'm going to leave you with this one last thought to chew on. The next time you dream about going to the moon, or maybe even Mars, remember that your weight will be completely different. You'll feel lighter, you'll be able to jump higher, but there's one fundamental part of you, the very stuff you're made of, that will be exactly the same no matter where you go in this entire universe. And now, you know precisely what that is.